Again, my name is Bill Phipps, and I'm one of the designers of the wolfHSM product. And we're going to be talking about how it can be applied to hardware security modules that are within automotive types of applications. Obviously, with HSMs, there's a lot of other applications we could use those in, but we're going to be focusing mostly on real-time automotive HSM solutions today. This slide deck is also available upon request. So if there's something I skip or something I miss, feel free to reach out and we'll be happy to share the whole slide deck with you. So let me just jump in. Opening question. A lot of people ask, what exactly is a hardware security module? And we need to be careful when we describe our solutions as well to make sure we're talking apples to apples instead of comparing it against other types of devices. From wolfSSL's perspective, an HSM, a hardware security module, is really a protected and separate execution space. Generally, this is done with an extra processor, but sometimes it's just done virtually as well. The entire point is the fact that you now have a programmable area that you can perform secure operations in. And generally, we see HSMs have cryptographic co-processing as well as secure storage support as well. Now, depending on your security requirements, that secure storage may be all you need to accomplish. Just leverage what the hardware provides to you, or you might need to add some additional confidentiality and authentication using our crypto software to make that secure storage work what you want it to do. We also see in the market many of the HSM enabled products tie the HSM security core with the secure boot sequence as well as environmental monitoring, and then the ability to respond to potential tamper events within that secure context. At the end of the day, what we are finding is that the hardware is definitely available, but sometimes it's difficult for the software to be able to use this hardware in a cohesive security solution. So we really see the current product offerings as kind of a hardware-enabled toolbox, meaning that all the parts are there, but it's sometimes very difficult for our customers to take advantage of that. Comparing an HSM solution with some other types of secure elements or other secure solutions, we do see a distinction here. And I'm just going to provide a quick comparison between trusted platform modules, which is again a separate hardware component, separately spec'd, and likewise compare that with a virtualized or a TrustZone based solution. And we see the HSM, because it's a separate execution context, kind of has characteristics of both without necessarily any of the bad things. From a TPM perspective, it's not user programmable at all. It implements a fixed set of algorithms, and it's up to you to meet the APIs to talk to it. It's also not generally tightly coupled to the processor, meaning there's a bus between you and outside of your chip to get to the TPM. And that may be a challenge from a security perspective. Obviously, TPMs do provide hardware crypto and a good protected storage. For that, tamper response is only partial because, again, it's not tightly coupled with the system, but the TPM can protect itself, which, again, in some security solutions is sufficient, and others, they are not. Hardware crypto on TPM typically is not done for performance. It's done strictly to handle just that last piece, perhaps an authentication or a signature or key storage, but not, although it can do the crypto, it's not really designed for that. Contrast that with a TrustZone or a virtualized solution, where in this case it is fully user programmable. You're given an extra context to work within. It is absolutely tightly coupled to the processing or the main application cores that you're dealing with. But generally, the TrustZone or the virtualized solutions don't offer any specific hardware crypto acceleration that the main processor doesn't already have. I listed physical protection as partial because yes, many of the hardware implementations of, let's say, TrustZone can support separate address spaces, but it's really up to you to make sure that you leverage those memory management features to protect address spaces. And sometimes breaking things down based on address isn't the right way to break it down for your solution. TrustZone and virtualized solutions, they don't offer any reasonable type of storage nor tamper prevent. In fact, if you take a look at how opt-t works in the TrustZone A solution, non-volatile storage from the secure world actually has to be stored through a non-secure world to gain access to non-volatile storage. That's not a necessarily good strategy. So we see the HSM as kind of filling the gaps there. Yeah, it's user programmable. Yes, it's slightly coupled hardware crypto. Many of the HSM products that we say or that are claimed as HSM products do provide that, but it's not ever a full suite. And so we do find the need to do some software implementation as well. Obviously, most of the HSM products out there do provide some physical protections as well as non-volatile storage, and generally they do hit tamper response. So we're starting to see that the HSM is kind of a different beast. It's not a secure element like a TPM. It's not just a secure address space like a TrustZone or virtualized solution would be. It's its own beast, and it needs to be treated that way. From our perspective, we saw that functionally automotive HSMs need to have the ability to do certain pieces, which number one, it has to be involved in the secure boot. We have to make sure we're authenticating many of the critical code sections that are within the HSM server itself, as well as in the client application codes. And really, as part of secure boot in system update, the HSM has got to be involved with that. And ensuring features such as rollback prevention is certainly an important system level goal to do that. HSM is typically the only component that can handle securely controlling those types of security features. Typically, we see HSMs are also involved in either the calibration of the configuration and protecting the data that goes with that. So this allows your application to have a certain set of features that are only enabled as long as HSM says those features are enabled. Single build without having to remove code, that's a better solution for everyone, but you don't have to worry about the feature enablement being broken and customers gaining access to code they shouldn't have access to. Obviously, HSMs should be providing cryptographic operations with private key material as well as asymmetric encryptions and hashes and signatures. Many times that needs to be the only thing that can understand the keys themselves. The private keys that were provisioned into the system can only exist on the HSM and it can't leave. Otherwise, that'd be an issue for your security solution. But the cryptographic operations that most folks are expecting out of an HSM are more high performance, have a deeper number of modes that it would support, but really well beyond what a TPM or even a PKCS11 crypto-key solution would provide. Again, those are low bandwidth with limited crypto functionality. HSMs, by their very nature, should have much higher performance and the ability to be updated there. Is most HSMs we see in the market have to be in control of the product lifecycle, including debug and test interfaces, as well as secure storage for, let's say, failure analysis, or if there was a tamper log necessary. The HSM is likely the component that's going to handle those things. At the end of the day, the HSM also has to be able to not interfere with real-time and safety critical requirements to make sure that it's working in context with that, supporting those types of executions. From our perspective, we kind of broke down an HSM as a system at top level looking down and as a logical piece. Now, this map happens to work pretty well for a lot of the existing solutions out there, hardware solutions that claim they are HSMs. And let me just walk through this because we're going to hit this a couple more times as we go. Left-hand side is what we would claim is a secure area or an area that is isolated from the HSM's perspective. We generally see a CPU that's sitting there that has the ability to be programmed. It's running out of normally local RAM and has access to local NVM that's used for both code storage as well as data storage. Typically, we also see crypto acceleration that's only tied to the HSM core, and then a series of custom controls, which would be things like JTAG enablement, IO access for, so let's say, tamper responses and detections, and things like that. But these, again, isolated and only given available to the HSM core. You'll see many times that the memory management units and TrustZone solutions are only tied to the HSM core, or at least a separate core that's designed to isolate access to the address space controls. But the key elements here is that there is definitely a local RAM. There's definitely a local non-volatile storage. And as the HSM core is a server in this type of logical breakdown, it's communicating back with application cores via a communication buffer. So this means your core needs to have some way of communicating. The HSM core needs a way to communicate with the application cores, and that generally is through shared memory or communication FIFOs. But it's a communication path where you're able to have the core request services of the HSM application cores request those services, and likewise, the HSM can go back. Very often, we see in tightly coupled systems where the HSM core has direct memory access to not only a shared memory space, but even many times dedicated local memory for each of the cores as well. Likewise, in terms of accessing volatile memory, HSM cores generally are able to access the non-volatile memory where the images and the data that the application cores are using is stored as well. In our logical model in the non-secure area, we see multi-core. Usually those have multiple different types of RAMs available to them, but we've got some dedicated RAM, and they're each running a user app. It might be a coordinated user app, it might be totally disparate user apps. From our perspective, we set up logically the HSM secure area as a server. It'll do a bare metal boot and jump into a communication loop to service requests. On the client side, we see this broken down as providing an HSM access client. It's a library that you would link against your user application to be able to issue requests through the communication buffers to the HSM core and get your request in. So that's logically how we see these breaking down. But we actually can apply this to a lot of other types of solutions here. So right off the top, we see certain types of things that look and smell exactly like what we expect an HSM solution. A system on a chip, we've got a dedicated security core and resources, and we see some examples, a TriCore, the SPC58 Bernina series, as well as the RH850. These are all existing system on chip solutions that have dedicated HSM style CPUs and cores. And these map really well to what the picture we just saw. We also see, a good overlap with this general model with configurable SOCs, things like a Zinc or a Versal solution, even a Polar Fire type of system on chip, where you've got the access, or you've got the availability of a large number of processors, soft or hard, that you can use memory management to isolate one of those units to act as a secure solution. Like in the Zinc MPSoC, you've got, a set of application cores that are, heavy ARM V8As. And then likewise, you've got some smaller real-time cores that are designed to be isolated through TrustZone solutions. And this is a model that we want to fully support and help to abstract from what the goal of doing the cryptography is there. We also see embodiments completely in FPGAs where everything is soft. You can draw the memory buses as you see fit, and then you can have this memory solution or this software framework work on top of an arbitrary type of solution. Obviously, on a single core, when you've got an ARM trusted execution environment or a TrustZone, either on the A's or the M series, this is a virtual or isolated solution. And we want to make sure wolfHSM can map onto that as well. So once you've solved your problem logically, we can help map that to even those types of isolated spaces, and even all the way up to a user space application where you've got multi-processes communicating, or even threads within the same process that the breakdown makes sense, even if the physical hardware isn't there to support an HSM. The logical breakdown still makes sense. So the point here is that wolfHSM by itself is a software framework. It's designed to be able to be mapped and ported to multiple actual physical hardware's solutions, even if it doesn't look like a standard HSM, we can probably still make it look like an HSM. From our perspective, wolfSSL, we've been in the cryptography business for a while, and we leverage many of our products to provide this integrated solution with wolfHSM. Obviously, our wolfCrypt product is a full-blown, very mature C-based software implementation of every crypto algorithm known to man that's been certified through FIPS and many other types of things. And we support just about any crypto that's out there, and we've been ported to just about every single hardware CPU known to man. Our wolfBoot product provides a bare metal bootstrap, and so we couple the wolfBoot with our wolfHSM to ensure that our servers as well as our clients have a secure, measured way of booting on arbitrary hardware, where we enable just a bare minimum of hardware to support a bootstrap. This means that we can actually boot systems with a lot smaller space than, say, a U-boot solution would be, and still maintain security because we've everything's hard-coded into the boot loader to ensure that there's no attack surface there. We support Wolf TPM, which is a TPM implementation, and we can support crypto callback, which this is how we handle offloading our crypto operations to other hardware, whether it's inside the HSM solution or outside, like a TPM. PKCS11, this is our interface that allows us to look like a PKCS11 provider, as well as we can issue requests to other PKCS11 devices or interfaces that are available on any type of hardware. And then lastly, because we implement software, we have implementations of the post-quantum algorithms, all the latest ones that have been reviewed, as well as we have some experimental ones that haven't been approved yet. We also support the ARIA and the Shangmi ciphers. So if you are working in any non-NIST style crypto, chances are our Wolf Crypt has that implementation of that crypto for you and provides, and we can run that on our HSM solutions there. From our perspective, when we started off Wolf HSM, we wanted to make sure from a design perspective that we stayed open source as much as possible. This is a double win for our customers because not only do they get to try the product out, with a permissive license on whatever hardware they've got available to it, they also get the ability to verify the code is written the right way and it's meeting their quality requirements, as well as can be modified to meet their specific requirements. And this is something that's important to us. Open source to us is saying, hey, this is not just what we do, this is how we do it. And so it's important for us to share that. So our goal really was to make sure everything stayed as open as possible. That being said, there are some hardware architectures that require NDAs to gain access to some of the secure features. Now, we've signed those NDAs on behalf of our customers, and so we do have other implementations that are not public on different ports that are available upon request, and we just have to verify NDA status. But again, the NDAs are there to protect the hardware. We believe the implementation of software on top of that should be as open as possible to permit review and quality controls. From our perspective, also, Wolf HSM is filling in those missing pieces. So if I've got hardware that can, let's say, do AES 128, but I need an AES 256 to do some certain feature, this is where Wolf Crypt can step up and fill in those pieces that are missing. We also find that sometimes the penalty to set up a hardware encryption solution is such that it takes longer to set the operation up than it takes to execute the operation, and we might as well have just done it in software to begin with where possible. So having software implementation of crypto also is a good option to maintain performance, even not only just for the large messages where the hardware is going to win in performance, but also for small messages where typically software can start and finish the operation much quicker. The third main design goal was to ensure that we had a common API, so that as you're developing your software, that it's portable between the different hardware implementations and the backends that we have, but also that you can test, as a unit test on your desktop without having to change your code significantly. And so you'll see as we go through the design how we've isolated hardware and port-specific information out of the main library. Obviously, support for asynchronous and time-limited execution. That's to meet our safety and real-time goals. We're very careful on static memory allocation. We don't depend on any dynamic memory allocation. If you've got it, great. If you don't, that's okay too. And obviously, being able to make sure that we can tailor out all of those features that you don't need. If there's no reason to include the Shangmi ciphers if you don't have a need for that. Let's get that out of that. So because you have the source, because you have the ability to customize that, it also means you can remove those features that you don't need, which really does reduce your attack space. Obviously, being able to modify the code yourself is important, and so we did provide user extensibility, which allows you to add in additional functionality without having to change our code. You simply link in callbacks, and then we can trigger certain messages to trigger your callbacks. And this is really good for certain operations that generally you use in sequence, but there's no reason that they would be ever grouped in that fashion. You can add that function to the server, the client can trigger that and get this exact sequence that you want with a single call rather than having to do it through a series of calls. And again, that type of extensibility was important for us. And then lastly, making sure that we always had a POSIX-based simulator. So even when you don't have hardware, the hardware's never been invented yet, or you want to do unit tests, you can always run all of your crypto, off of your desktop. Again, functionally, we broke this into a client and server. I'll skip some of these bullet points as we get to some pictures. and start to explain how this all works. So from our perspective, we have the applications that are requesting services. We call that the client. It's linked in a wolfHSM client API, which provides communication access to the HSM server, as well as some other features we'll get to in a second. But the goal here is that you have an existing application that perhaps is using, let's say, AutoSAR SHE or a PKCS11 or some other type of, even an OpenSSL style of crypto that you've already coded up, and all we want to do is add in the ability to bring that client functionality to offload that. This is again going to talk. This is mostly this entire API is not port specific. It's agnostic. So you're going to write your application once to the Wolf client API and our Wolf Crypt APIs to do all the crypto, and you won't have to change it after that. The only thing that changes is this port specific communication feature. This is how you communicate with the HSM server. And again, this is a multi-core designed to support the server can handle multiple sessions at the same time from different cores. But that one piece is what's custom. On the Wolf HSM server side, we run a server application which provides non-volatile memory storage, which is more than just keys, by the way. You can store arbitrary user files and data in there as well and have that under the same type of protection as your key material. Supports a key manager, which allows us to bring keys out of non-volatile memory, use them for operations, and then securely wipe them, as well as a full-blown implementation of Wolf Crypt with hardware offload. And all of this is bundled into a separate executable that implements, obviously, the communication path as well as any port-specific interfaces to the hardware. From the client perspective, we break this down farther. We have an API, which the API wraps a series of Wolf Crypt calls. Again, Wolf Crypt is all of the crypto known to man sitting in one library, but the Wolf HSM client sits on top of that, allows you to access any of the crypto, and only when you'd like to, you can have full local software crypto implemented, or you can offload that crypto. And we've got some API examples I'll get to that show how to switch who's doing the work. This software crypto as well, this is a local implementation on the application core. You can tailor that out. You can make it as simple as possible so everything goes through the client, or you can bring some of those operations local that maybe aren't as sensitive, but may perform better. And SHA is a great example of that. Many times we see application cores are higher performance cores than the HSM cores. And if you're doing a non-sensitive operation like doing a SHA measurement, it may make a lot of sense to run that locally from a performance perspective, and then leave the HSM just to do, let's say, an asynchronous signature on top of that. So the Wolf HSM client also provides key management for not only local-based keys, but keys that are only stored on the HSM client. And from a key management, the client doesn't have the contents of the key. It simply uses a key by an identifier, an ID number, and that's how it indicates to the server which key to use. And then likewise, a non-volatile memory manager. So any non-volatile memory that it'd like to use goes through a client, and it goes through the server, and the server provides the data back as necessary to the client. So again, from a functional perspective, all of these components are generally non-port specific, meaning that once you've written your code once on the client side, you don't have to change it, because the only thing that really changes as you move between hardware pieces or from test into implementation is these port specific. And again, the only thing that we need from the client perspective is how to talk to the HSM server, which is normally done through a series of interrupt flags or a communication buffer, but this could also be FIFOs or even communication sockets if you wanted to. From the server perspective, it's a similar type of structure. The server itself, though, does its own bare metal boot. It jumps into an image manager, which gives us a context to test not only our own image that we're running out of on the server side, but also the client images, if that's something that's necessary to support a measured boot on the overall system. And then after all that, it jumps into a server loop, which is just basically looking for requests coming in. The server, again, open source, you have the ability to add your own code to it. So there is a full-blown server API that works within that. Obviously has access to non-volatile memory. Typically, the HSM flash is different, or non-volatile storage is accessed differently than what we would term as a main flash or the client flash. And so normally the HSM server has accessors for both of those. Supports a key management. Sometimes the keys strictly are in the hardware side of the house. Other times we just manage the keys locally. And again, they may be backed by local storage as well. So the key management is really saying, read the data from the non-volatile memory, use it as a key, and then you can have an index value associated with that key. The server also implements a full-blown and tailorable version of Wolf Crypt, which allows us to have that software crypto that can fill in the blanks and then it can choose when to offload certain operations to whatever hardware is available. The server side is the one that really has the more heavy lift to do in terms of porting. And so you'll see that from the server side perspective, we see the custom controls are always platform specific, typically interrupt controlling, the flags and the communication buffers, those are all hardware specific, as is the interface for any hardware crypto from an acceleration perspective or a keys perspective. And normally we find non-volatile memory management is something that's port specific as well. So fundamentally, that's how we've broken down those software modules. We do want to point out that everything we're talking about here, we've been in the AutoSAR crypto stack for many, many years. Our wolfCrypt product by itself is used in a lot of other people's products, and it's designed in the same way wolfHSM is designed in the same way to support asynchronous operations as well as abstracted and layered designs, which again, this lines up well with AutoSAR. We can sit within an existing AutoSAR driver. We can expand it to provide AutoSAR crypto drivers or all the way up to a management solution. And so the wolfHSM client side really has that ability to fit into your existing solution, or it can grow to be its own full-blown drivers. We do want to also point out that the AutoSAR stack, it does have limitations on how its API works, which may not take advantage of everything that the wolfHSM APIs can do. So by limiting yourself to the AutoSAR mechanics, you might find that, oh, I have to do 3 series of calls when in wolfHSM, I would have done that, move that function out to the server and done a single call. So we find some limitations in the AutoSAR APIs as well. I'm going to walk through a couple of examples of how this works. Again, these are client-based examples, so I'm going to skip a couple of these slides here, but I want to get into some APIs as an example of how we wanted to implement and how we did implement the ability to move where the crypto is happening. The left-hand column, this is just an example of using wolfCrypt calls alone that set up an AES context, set the key material in that context. In this case, we're doing a simple CBC encryption, so we just need the key material, which is listed here. To perform the AES, I actually have to have the key material. And the initialization value for this is CBC. We invoke a CBC encrypt function. Plain text goes in, ciphertext comes out, and then we clear out the context when we're done. So this is a very typical use case for just doing a simple encryption, CBC encryption on client side where you have key material. Now we want to switch this up. Now maybe this private key isn't known by my client, but the server knows it, and we identify this as an integer. In this case, it's just we called it key number 1. What has to happen in your code is obviously when we initialize that context, we make a change and we say instead of doing this invalid device ID, which says definitely do local software implementation, this says, hey, offload this to the wolfHSM device. So change number 1 is just to, when you initialize your context, you're going to point it to use the HSM server instead of doing the work locally. The second thing is we wanted to say, hey, in terms of this context, I want to use a key that is only known by the server. And this is exactly what we do. We said wolfHSM client call that says, hey, I want to set the AES key with this context to be this key ID number. I don't have the actual key value. That's only known by the server. But I do know that it was key number 1 that I had loaded into the server to do this encryption. We set the IV a slightly different fashion than the set key, but it's the exact same type of wolfCrypt command. And then we invoke the exact same wolfCrypt AES CBC encrypt using that context that we prepared. Same ciphertext, same plain text. These are all local pointers to me, and we perform a free. So in terms of being able to offload the exact same sequence of commands, it was really just a handful of lines of change. We changed who the context was going to be associated with, which device, and then instead of knowing the key material like we did on this left-hand side, the right-hand side we said, hey, we only know it's a key ID, and this allows the HSM to securely keep that private key material, and the client has no idea what that material is. Now, if this was an AES that the HSM server could enable with hardware acceleration, it would choose to do this in hardware. If it was an AES solution that maybe it's a mode that's not supported in hardware, the server would then implement that in the software, and you'd be able to basically do whatever you wanted to do on the client side without being aware of what the server can and can't do. I'm going to skip this example as well. So I want to kind of keep moving forward with the rest of this. Is just a slightly different example. If you get a chance, this is where we load key material into the key cache on the server. do the same sequence of commands, and then afterwards we blow that key away. So this is an example. Let's say you've generated a key locally that you want to temporarily load to the material. Again, I'll switch out there. From a non-volatile memory management perspective, all of the items that we use within Wolf HSM on the server side are stored when they are stored as a non-volatile memory object, which allows us to associate certain metadata along with any data that's being stored. And the data could be things like certificates. It could be key material that's raw, or it could be user data that the HSM doesn't even understand what that is. And so that metadata allows us to identify that, index that, and then provide access controls and other usage flags associated with that that make sense. I'm going to skip all these NVM meshes because this talks about how we do um, or we do fail-safe reads and writes to Flash even when that's not supported. So as an example, I'll just plow through what this could look like, on the client side. So in this case, we're just initializing a client context. There's a couple other parameters I skipped. We'd like to associate this metadata, which happens to have an ID value and some sort of label, with this piece of data. The call here is just to add that NVM object in with the metadata that I've associated with, and then the actual binary data. And at this point, the client will actually send that data to the server, and the server then would store that in NVM and is now in the server's NVM storage. If you wanted to update that, you can use the exact same metadata object and add that, which would eliminate the previous version of that object and make the new one available. And then obviously a cleanup. So again, it looks just like a simple file storage. In this case, we're just storing arbitrary data, but for keys and certificates, we have other APIs that set the flags so that the server understands that, hey, this is key or certificate data. And then again, all of this metadata, this is up to the user just to define, aside from a handful of flags that we've predefined. Let me keep moving on through that. Let me talk a little bit about how we deal with the secure boot sequence on most of these chips and how wolfHSM can be used into it. And so we do see a number of different strategies. We got a lot more moving parts now, a lot more ROM-based solutions that we have to deal with to support a measured boot sequence on an HSM device. But let me walk through a couple of those types of integrations to see if there's we can kind of point out maybe some of these match your use cases. From our perspective, wolfHSM alone, you may be on a platform that has a very secure ROM bootloader. Let's say you're on a Zinc MPSoC where you've got a CSU processor that is actually able to securely load images into either your application cores or your real-time cores. So that may be sufficient to meet your security requirements. The only thing we'd have to do is to make sure that the server actually comes up and starts to execute. There's a communication path there, and then the client applications can again use the ROM-based solution. So in this case, wolfHSM doesn't have to be involved, and we don't need another product to support a secure boot because we're going to just trust the hardware. Again, this is the simplest, the opening solution, and it's viable for those hardware platforms that have an infrastructure that can support a secure boot. What we're finding more likely, though, is that most of the systems have a limited amount of secure boot solutions, or they can measure up to a certain point. And we'd really like to be able to support in-system updates as well. So we couple our wolfBoot product, which provides local key material, which can then protect the wolfHSM server image using that key material. Now, this would be private material that you would generate at compile time, associate that with the bootloader, and then you would sign your wolfHSM server image. And only if this image is undamaged, would it actually jump into it and start to execute this. So from one perspective, we can secure the HSM server side using wolfBoot. wolfBoot also allows in-system updates. So once you've got the system booted, initially with wolfBoot, you can update those images, provided they match the key material that was baked into it, and you're allowing yourself to update the server side. Again, from the client perspective, it could still use the ROM-based bootloader and then provide a wolfHSM client who's now talking to a secured by local key material, not just the ROM bootloader. can talk to that server. So again, it's a step in the right direction. We can also do the opposite, where you use a ROM bootloader. You trust the HSM server side of the house is going to be secured by ROM. It can hold on to key material that now when the ROM bootloader starts to boot our clients up, we actually teach wolfBoot how to talk wolfHSM to get the key material. This allows you to do a secure measured boot on the client side using client applications, client side wolfBoot, but the key material only exists on the server, which makes sense. This matches the deployment strategy for many of the HSM products that are out there today. And again, we're protecting the final client application code, which is updatable via wolfBoot, with key material that we've stored specifically in the server. Again, this is a better model, and this matches a lot of existing solutions. Another solution would be to combine those two pieces where you now have an in-system updatable version of the HSM server code, which is protected by the yellow keys. This HSM server is holding on to the green keys, which again, this is what the wolfBoot on the client side is using to protect the client application. So you can start to see there's a lot of variations of how these different products can work together to meet whatever your security needs happen to be. And we provide one fifth model here, which is where we integrate on the server side the wolfBoot and the wolfHSM server into a single executable. And instead of letting the ROM bootloader trigger the clients to boot, we teach the wolfHSM server how to specifically release each of the cores and perform that without relying on a ROM bootloader sequence. So this allows you to break the connection, ensure that the wolfBoot is intact based on private keys that you generate yourself. And this also allows you to have separate keys that manage the client application. Now, this is really what we see as the target architecture for many applications, where the ROM bootloader is only enough to secure the HSM side of the house because it's a separated space, and the rest of the client needs additional support to support a truly secure boot in a measured sequence. And again, this is using key material that the wolfHSM server has. So this allows you to put your key material in instead of relying on anything that the ROM is providing. So again, how wolfHSM can be used as to meet the secure boot requirements really is a function of what your final application solution space looks like. But we are able to fit these in multiple different types of strategies depending on what your hardware is and what your security requirements are. And that's really the goal, was to make sure we had a flexible framework that could meet changing security requirements. Let me jump into how we do porting and testing on this. Because we've been careful on how we've segregated out the different client APIs to make sure that there wasn't anything port specific. This allows us to use only standard development hosts when we're developing our wolfHSM clients, and even the server changes the logic that we would, let's say, put custom logic into here. You can just run this on your desktop. We support any POSIX processes. We support multi-threaded implementations. In fact, all of our unit testing for wolfHSM, we use unit testing on our POSIX ports. This also means that you can start your development of the logic that you need in a completely agnostic virtual sense without ever getting the hardware that you have to eventually port to. In fact, we think the development of the application, wolfHSM application in your client, it should happen well before you get hardware, unless you're waiting on hardware to understand where some of those breakpoints in performance might be. This allows you to run both the server and the client. We support even things like TCP sockets between the client and server processes if you want to run them on different processes, or shared memory systems if you want to, or multi-threads in the same architecture. Again, logically, the wolfHSM model works on all of those. When you're ready to actually get to hardware, this is a giant step. You take your exact same code, you instead modify it to say, hey, I would like to use the port-specific bottom end transport access from my client application. And then you go back and then rebuild your server application, this time with a server that whatever that architecture is, that's port specific, as well as whatever hardware they've got. There might also be some non-volatile memory management and key management pieces that are port specific. But again, those are isolated to just the server side. Your client side did not actually have to change except be recompiled with a different bottom end. And we find this model is definitely useful, not only from an early development stage when you don't have hardware available, but also in a unit test stage later on when you're making sure that your logic is working the way you want to. And again, if you want to run in simulators, we fully support simulators as well. I do want to point out that we have a number of ports that are either in progress or have been released. So these are actual ports. These are things that you can get today. For the Aurix, the Infineon Aurix series, the TC3, which is very similar to the TC2 if you're already using that. We do have a full port available for both the client and server. We did support all of the crypto offload that it can handle, which is a true random number generator, AES-128. Some of the elliptic curves to the 25519 curves as well as parts of SHA. That should be SHA-2. That's their support for hardware is a little bit limited, so we kind of fill in the blanks when we notice that a request comes in that can't be offloaded to hardware, and we support that. The TriCore's, or at least the Aurix platform, is also a good example of where you can have totally different architectures on your application side as on your HSM side. For this system, they're using a Cortex M3, which is an ARM-based architecture, and on the application side, it's TriCores. So you end up with this cross-platform type of solution to make this all work. We also support the STC, the STMicro SPC58 series, specifically the Bernina. This also has different architectures on the client and server side. The PowerPC on the server side is a much weaker version of this. In fact, it doesn't handle even things like cache inside the chip. So this port is available as well, and they had a slightly different set of crypto offload available on the STC. And we're just about done with our RH850 port. That's actually in test right now. And this is the F1 series. The U2 series will be coming out soon afterwards. This is designed to talk on the ICU-M series, not the ICU-S series of HSMs, where you have a separate core that's running. Again, it's just a slower version of the main cores that they've got, slightly weakened as well. But it does support full crypto offload of the random number generation as well as AES-128. Again, so it's the same base wolfHSM able to port to these very popular HSM style vendor solutions that we've got. Again, from a porting interface, the things that we care about, non-volatile memory access, the crypto hardware, obviously, and then fundamentally on the platform interface, typically boot sequence and how we handle application cores, either coming in or out of reset, really is there. The other thing we find is that sometimes the HSM specific memory is very limited. So it may end up limiting what applications or what types of crypto we can perform on that. So you might see mentions of Evita medium versus Evita full. That really relates exactly back to how the memory limitations limit you in terms of types of algorithms you can implement in software. I'll skip through this configuration because I'd like to get to some demos. All right, as I've got two demos ready for you today. The first one is we're going to walk through some of the bottom end pieces of wolfCrypt and on a TriCore 367. This is a dual core version of the TriCore Aurix. There's two TriCores and there's one HSM core. It does support a series of offloads. In this demo sequence, I'm going to walk through how the cores initialize to each other, and then we're going to walk through parts of our standardized wolfCrypt test and our wolfCrypt benchmark. Now, the wolfCrypt test is the same test program, and the benchmark is the exact same one we run on all of our different platforms when we implement the crypto on each of those platforms. In this case, the wolfCrypt test, the server has been configured with one set of instructions and the client's been configured with a different set of algorithms. This test is, again, a known answer test, and it's demonstrating that we can perform all of the crypto on either core running software, and you get some benchmark numbers to go with that. We also, in this test, will be showing out how we can interface to the hardware crypto features, and we'll show some of those custom callbacks as well. So let me jump into this. Again, logically, this system maps exactly to our logical diagram. Today, we're only going to be using a single one of those cores to issue requests and run those things. Just as a heads up on this system, all of the printfs that you see are actually generated on, let's say, on the HSM core and then sent over to the core 0, where that core is actually allowed to talk to the serial port. So anything that you see that is generated output, it's either from the primary core that we're using for test or from the HSM that's been routed through that. The HSM core doesn't have direct access to the serial port in this case. We built all of these with Aurix Dev Studio. and using the openly available GCC for that. In this case, the TriCore, we did enable what we call our SP Math library. It's still a C-based library, and on the ARM side, we are using our optimized assembly version of wolfCrypt that's specific to the Cortex-M. So let me this is the output. Let me switch over and we'll watch it live as it goes. So let me just hit a reset button on this guy. Now this is oops, this is this one. This is again a 367. I'm going to hit reset and we'll just watch it as it runs through the test. So let me scroll back up and start that test at the beginning as it's running. So as it first comes up, you'll see the TriCore initialize, HSM initialize. This means the TriCore client core is now talking with the HSM core. It's just a quick communication message back and forth. Now we run into wolfCrypt test again. This is a standard one. This is running software-based solutions on the TriCore application itself. And we report, hey, we're running version 5.5 of wolfCrypt on there. We plow through a number of known answer tests, randoms test, hashes, HMAX SHAs, AES. Generate an RSA key that's in there, perform RSA testing, ECCs. And so at the end of the day, these are all known answer tests. It's not designed for performance. It's designed to prove we're getting the right answers. And this is all on software on the TriCore side. Once that's complete, then we jump into our standard benchmarking, which again takes every algorithm that's been compiled in and attempts to run it for about a second to check the performance. And I'm just going to point out that first entry, the AES 128 CBC encrypt, we're seeing about 3.7 megabytes per second. This is the TriCore using local data to do encryption. This is what you would see if you're doing, let's say, a TLS session using only the TriCore core to do that. I'm gonna, oops, let that go back. I'm gonna also point out, let's take a look at that ECC Prime 256. This is doing key generation. So again, this is about 30 operations per second of doing key gen, which is reasonable for a 300 megahertz microcontroller. But the point I wanted to make is that this is using the Prime 256 curve. This is the way we've configured this client to work, and you'll see that this makes sense in a second here. So we run the exact same tests after we've run it on the TriCore. This is just another test that now we're running everything on the ARM. And this is the HSM. All of the output you see here was generated by the HSM and then routed through the TriCore so we could see it. So on the HSM side, we're actually running a later version, a 563 version of wolfCrypt, and we walk through all the exact same sets of tests that we've got. It's actually generating RSA key right now, which is kind of slow on this 100 megahertz ARM Cortex. Oh, it just finished generating the key. And we'll let it finish off this, then we'll watch the benchmarks run. But the point being is that it allows you to select those types of configurations that make sense for your architecture and then tailor out everything else. So when we did, this is again all software based, AES 128 CBC encrypt on that 100 megahertz ARM that has limited cache, we see a much slower performance, about 288K per second, which that's not bad for a 100 megahertz Cortex M4 with limited cache. So that's not a bad number. We'll just keep letting this run. Again, these are live numbers, so if something were to happen, it would be proof that it was actually run live, and these are not, you may not get the exact same results each time. So in this case, it's doing, again, some RSA operations, which are challenging to do on that without hardware offload. In this, we also now show that we're doing ECC. This is a Prime 384 curve. Now, this is a different curve than what the TriCore had, which is proving that we can handle different configurations on the client and server, but also showing that we run all these different algorithms, in software on both sides. Finishes that. The last piece of this test was to walk through some of those same pieces. Now, for things like AES, the hardware offload, CBC is fully supported. So we actually ran a quick, that same AES CBC running in hardware, roughly the same types of things, but we're seeing about a 3.4 megabyte per second performance. Now, this is the ARM core asking the hardware to do encryption of data that's outside of where the ARM core is. This is a small message test, which is likely of what we're seeing. And so you can see much higher hardware performance as the message size gets larger. But the good news here is as we ask the HSM to do a small message test, we're seeing roughly the same performance, almost, almost the same as what we see on the TriCore, but it's done completely by the HSM server. The TriCore is free to go and do other work while this work is going on. Other parts of the hardware acceleration are components of pieces. So if you'll see things like the elliptic curve operations is actually a sequence of that. So we are simply running known answer tests against those to prove that those pieces work when done in hardware. So again, this is just again a crypto test showing that we can control both of the cores. We can run everything in software on both sides, can be configured differently, and gain access to the hardware offload. Let me switch to the next demo that we've got. And again, all of these pieces are sitting here. We wanted to really point out the ability that we can access hardware and then change things. So this next version is against a TC375, which has 3 application cores, similar things, but now instead of doing just bare wolf crypt calls, this is all implemented as a wolfHSM client and against the server. And we're going to do a couple of things. We're going to do a quick echo test, which just sends a message and gets the same message back. We'll demonstrate that the client can insert a whole bunch of NVM objects and then retrieve those objects and then delete those objects. We run through a RNG test. And then likewise, we do a client RSA request to import a key, commit it, generate a key, export it. So this is standard key management against the server's NVM. The last piece we do is we taught this server how to do 2 additional tasks. One which was disable the Ethernet port, and the second was to disable the JTAG, the debug port. And again, these were implemented as custom callbacks, so the client can trigger the server to execute that call, and then the server goes ahead and does that. It could be anything you wanted to. We simply made the example of these 2 pieces. So same type of thing this time with 3. And let me just switch over to that demo real quick. So this is running in the other system. Let me hit reset as we go. And this happened a lot faster, but let me scroll back up and I'll show you the beginning of what happened here. All right, so at the top of this is well, this is where this test started. I should have probably cleared that before we started, but at the beginning, we are simply doing a communication buffer, and we're simply showing how we had configured the client to talk to the server, which is again a series of memory addresses. We trigger the HSM initialization, which is an interrupt back and forth to make sure both sides are up and talking. And then we initialized some of our crypto context. Again, these are all HSM calls. They're fully abstracted, and I'm not using anything that's custom in the test code. In fact, this test code that you see running on the client side here is the exact same unit test code we run as we are checking things out. So we just picked up the exact same code, dropped it onto the TriCore, and ran. It walks through a series of echo tests that just somebody sends data back and comes back and then verifies things are working. It goes through a series of NVM calls, which is basically calling out saying, hey, you've got about 64K of data available in a series of objects. Then it adds a number of objects in and extracts those objects back. I'm going to skip down a little bit because some of these tests are wordy. Then it goes and destroys those after verifying that everything is working the way it's supposed to. Now, these are all unit tests. So this is exactly the same test you would run on your desktop to prove the library is working the way it should be doing. So I'm going to skip the rest of these. There's 2 different ways of doing the NVM data. One is I send you the data. The second is I send you a pointer to the data. So the second sequence was using DMA accesses to grab the data. So I didn't actually have to send it through the communication path. At the end of this, then we enter into a standard crypto test, which walks through getting random number generation. This is a sequence of calls that the server has to implement, but it's a single call on the client side. It says, hey, give me a random number. While the server has taken a TRNG, has seeded a DRBG, and then used that output to spit back answers. So from the client's perspective, he asked for a random number, 1 call. The server actually had to do a number of steps to prep that, verify the TRNG was in a good state before it could provide back the answer. It does a series of key cache and exports, evictions, as well as key gens. Again, it's just asking the server to do these generations, and it gives us the answers back. The client didn't have to do any cryptography to do this. It was all just message passing back and forth. And at the end of this test, again, this is just a standardized test. We implement custom callbacks. And again, if I had a JTAG tester on this, you'd see once I hit that custom callback 2, the JTAG would die. And that's actually the test we run to verify that works. But at the end of the day, from the client's perspective, this is the exact same client calls that we use on every platform. to prove that things work out the right way. Let me switch back to the other screen real quick. And again, this is just kind of pointing out how those different tests work. And the good news here is that we just picked up the code and recompiled and went from there. So I did want to point out wolfHSM by itself. We were getting tasked by different customers to go to different architectures, but we also have on our own roadmap the ability to do future development and other stuff. So we found that our RH850 and the U2 series specifically is where we'll be moving to next on the Renaissance side. We're going to do from an additional port perspective, we're going to show how we can wrap a standard TPM using a Wolf TPM product as the back end and execute an HSM using just a TPM. We do find that we have customers who don't have the ability to have a separate execution core, but they still want to use the logical layout of wolfHSM to talk to their TPM. And we will be moving on to the Infineon TC4 series. We also have a series of microchip parts that we'll be porting to and making those available. We will be adding additional providers. Currently, we support PKCS11 from a Wolf Crypt perspective, but we haven't completed that port for the wolfHSM as a back end as a PKCS11 provider. So we'll be working on that this year. We'll be providing also client server encrypted communications in case you need to work over a path that is not stable or is not private. Which means that you could have your client doing crypto calls locally to encrypt the requests that go to the server. This would be something that you would use, let's say, over a serial line or even like a network protocol if you wanted to support remote. But by baking that into it as a standard transport option, it gives our customers some other options. Likewise, we'll be finishing off our full AUTOSAR crypto driver so that wolfHSM can be plugged directly into an AUTOSAR application. And kind of go from there. So that's kind of where we're going in the future. And if you want links to anything that you've seen today, obviously our main product page is off of our website. Everything that we can share publicly, we share on our GitHub, wolfHSM as the base library. We have an examples directory that walks through a number of different ways of using wolfHSM on different architectures, specifically ported using the POSIX backend, so it'll run just about anywhere. And obviously, wolfSSL, wolfBoot, and our wolf PKCS products are separate repositories that are available online as well. Well, that's all I had for today. Let's see if we can go through some questions from you guys. If there's anything I skipped over that you want to hear, or if you have any open questions you'd like to talk about.
Thank you, Bill. So there's one question. How is wolfHSM different than hardware vendor provided firmware solution?
It's a common question. So number one, let me go back to some of these slides at the beginning here. We're not platform specific at all. We do implement ports for different platforms. And so what you'll find, the APIs that are exposed from vendor-based HSMs tend to align with just what the hardware can support, as opposed to exposing a more full-featured crypto layer. So by not being specifically hardware or tied to a specific hardware, we can provide an entire suite of crypto algorithms, things like post-quantum that just don't have hardware implementations yet, in a compatible way. That means that as the hardware catches up, we'll be able to start to offload certain pieces of that to the hardware. So one of the fundamental differences, aside from being completely open source where we can be, than the vendors is the feature set. We support all of those, and then likewise we tie in to other types of either booting systems or hardware crypto systems or communication systems. So it gives us that flexibility to actually work on completely disparate types of hardware with a common API. That means that you aren't, as a customer, aren't necessarily locked in to that vendor's specific hardware. This allows our customers to now move between hardwares, pick the right tool for the right job without necessarily upending all of their software. So again, open source, number one. Number two, not hardware specific, so we can offer all those pieces. And then number three, there's no vendor lock-in necessary.
Perfect. There's another question. How much HSM RAM is required to run the wolfHSM code?
Oh, that's a great question. So really, we split this into two different pieces because we have, let me scooch back up a little bit farther, because we have both a client library set and a server library set. We split those into two different pieces. Now, the other thing to realize is that when we have Wolf Crypt available on both sides, this software crypto library, from a code perspective, can provide a lot of different functionality, or you can tailor that out and not provide that code. Some of the algorithms, though, do require amounts of RAM in either a stack or a heap. But we do try to limit our states to reasonable sizes. So as an example, we were able to do full RSA computations within an HSM on the ST58N series, which has roughly 80K of RAM total. And so we can actually execute all of the HSM code as well as still have stack space, which takes about 40K to do about a 30K or 72-bit RSA key to be able to execute that. So generally, we're finding our static space in terms of RAM usage on the server side somewhere in the 30-40K region, depending on which features you've enabled and how much cache space you want to give it. And generally, the stack space for almost all the algorithms, if we had a 40K, that'd be spectacular. But depending on which algorithms you have and which ways we've implemented it, we can reduce that stack to be much smaller. So you're in the say 80, 90, 100K region of RAM on the server side. And again, fully tailorable, fully configurable, and we have multiple implementations of many of the software algorithms that can do a space and speed trade-off there. On the client side, you've got the same type of issues, but generally we see on the client side, the ability to have a lot more RAM if necessary. So we can squeeze down to just in the 10, 20K region if we don't have any software crypto necessary, which is just enough to run the communication buffers and those interfaces. Or you can do a full-fledged software crypto where you might need, maybe up to 120 or 140K of RAM if you really want to do every algorithm known to man on the server side. So I don't know if that helped answer your question, but yeah, the point is it's fully configurable, probably no smaller than on the client side, 20K-ish, and probably no smaller than about 40K on the server side.
Awesome. Thank you so much. There's another question. What are the unexpected challenges to implementing an HSM-based product?
That's a good question. I might sound a little jaded. I might sound a little bitter about this, but I can tell you the current state of doing low-level debug on HSMs on many of the different hardware implementations is challenging. Access to documentation specific on the server side. Sometimes those require NDAs, and many times those documents are prototype or draft documents, and so it's sometimes very challenging to get working systems because the debugging is challenging, the documentation is challenging, and sometimes we're still working on first generation silicon when there's still bugs. And so the things that I have found most frustrating is again debug and documentation. In terms of fitting things in, once you've got a working build environment, once you understand the limitations of what the hardware can do, I found that the rest of the code comes together very quickly, and we can generate applications on top of that. But definitely that getting started part, getting over that initial part, that hump of getting a debug environment working, that was certainly a lot harder than what we're used to doing when we do hardware reports. It just seems that sequence is not quite as fleshed out as the main application core side of the house.
Perfect. There's a last question. How has the HSM product changed over the last year?
Oh, that's also very good. When we started Wolf HSM about 2 years ago, there was a handful of products, and the HSM solutions were very limited. You didn't have much of a choice to go with an open source solution. But what we're finding with new products coming out, we're seeing the HSM cores are getting more and more parity with application cores. They're no longer these crippled, tiny little versions of these security cores, but people are recognizing, hey, the chance to put code is a chance to offload some of this logic as well as crypto. And so we are seeing much more higher powered HSM core solutions. The second thing I would say is the recognition in the silicon side that security is no longer something you can add on at the end. It really has to be integrated early on. Is also a very welcome change. So we're finding more integrated solutions up front, really considering things like in-system updates and secure boot as being part of that, and the hardware is catching up in that regard in terms of how you provide an overall solution. So I'd say, higher powered processors, better recognition of what the security challenges really are, and then watching the HSM cores kind of grow out of just a cryptographic offload to more of a full-blown feature set, and that's where we really find that this is a good change. Security is no longer an afterthought; it's almost a forethought, which is great, and that's a nice change we've seen.
Thank you so much. Thank you, Bill, for hosting the informative webinar, and thank you everybody for joining the webinar today. You can keep up with our upcoming event, meet with team in person, read our blog posts, and get the latest wolfSSL update by following us on X, connecting with us on LinkedIn, and subscribing to our YouTube channel. If you have any question, please reach out to us at facts@wolfSSL.com. And thank you again, and we look forward to seeing you on March 26th for accelerating encryption with wolfSSL and STM32 NPUs. Thank you.